The floor is yours. Thank you very much for coming.
Thank you. Thank you, Patricio. I kind of wanted to wander around. Everybody can hear me okay? I kind of wanted to wander around with this microphone, and this podium won't really move. So good afternoon, everyone. Thank you all for coming. I'm real happy that you're here. I'm very pleased to talk about a little bit about the work we've done at Los Alamos, where I'm no longer. I'm now sort of semi-retired from there to be president of AWS this year. I appreciate Los Alamos. I haven't asked them, but they're letting me use, unbeknownst to them, they're letting me use their templates here for the overheads. And I'd also like to thank and point out my co-workers on this. You'll see here this photograph of a, it's not perfect, the seams here are not quite right, of a hexagonal heat exchanger there sitting on the build plate for powder bed. There's also tensile bars in the back there. We'll talk a little bit about that later. So despite the fact that Los Alamos is a weapons laboratory, this work has nothing to do with weapons, otherwise I wouldn't be able to talk about it at all. So we're going to talk today about radiation tolerant nuclear components. So this is a weird angle, but of course Los Alamos and the other national labs in the United States, many of them are run by the Department of Energy. So in the Department of Energy there is an NE, or nuclear engineering program office, and according to their roadmap document, they won't be happy. Hold on, I got to get rid of something here. There's a big message window in the middle of the screen that won't go away. So it makes it hard for me to read, sorry. I'll read off of that. So the key challenges to future reactors involve making improvements in affordability, so making stuff less expensive, and also trying to find ways to make the structural materials that are used to withstand longer life in service. So we've found out that laser additive manufacturing, or just call it LAM, is particularly well suited to making things more rapidly and also efficient economically, and also can be used to find new ways to fabricate some of the components. So our objective here was to determine feasibility for this laser additive manufacturing for making affordable components in this, I call it grade 91 steel, and it's a creep-resistant ferritic martensitic steel. That's what creep-resistant FM means. And it also has radiation tolerance. I call it grade 91. There's a P91, which is plate, and T91, which is piping, and I just call them together grade 91. So what we did was I acquired some grade 91 powder. I'll show you a little bit about that in the next slide. The abstract I think I wrote was incorrect. This is done on a EOS powder bed machine. I should point out that I now work for EOS competitor, Optimec, and so my employers wouldn't be happy if I said this, but they're not here now. Afterwards, we did a couple different interesting heat treatments. Usually when you weld the T91 or P91 plate or piping, it's now connected to a big reactor. It's very difficult to go back and heat treat that. So it's given what's called a direct temper. You see the parameters there, 770 C for 45 minutes or less. And also, if you wish, and you can take the part into a furnace and renormalize it, which is austenitizing and dissolving carbides, and then followed by the tempering procedure. Characterization involved light optical SEM, electron backscatter, TEM, and STEM. We'll talk a little bit about some of the tensile properties. Micro hardness probably won't cover. Nano indentation we'll talk a little bit about later. Radiation testing, I won't have much time to talk about that today. We'll talk a little bit about that during the nano indentation testing. The composition of grade 91, the specification is shown at the top, but basically it's a 9 chrome 1 moly, low carbon. Steel has little additions, small additions of vanadium and niobium to form fine carbonitrides during tempering and also at higher temperatures. Our material, that's nickel, I think. I can't read on the screen. The nickel was a slight bit out of spec relative to the spec. but nothing else unusual. I'm obliged because it's a powder to show you the powder distribution, nothing unusual here. The powder size, Lejeune, where's Lejeune? We talked earlier. This is, less than usually 45 microns in size. This is an important point to point out. So Lejeune is going to send me the other phase diagram he made up, but this I stole from this, Ayala chap. Pseudo-binary section through a much higher order phase diagram. Everyone knows what a phase diagram is? Anyone not know what a phase diagram is? Okay, pseudo-binary section showing carbon range here. This is 0.09 carbon, I'm sorry, right here. So what's supposed to happen during welding or additive here, where we're going to melt and resolidify, transformation should go from liquid to liquid plus delta ferrite, and then into the two-phase ferrite plus austenite region, a little bit in the straight austenite region. Now austenite plus carbide. Eventually coming down here, it should be the alpha ferrite, and it should, if you cool very rapidly from up here in the austenite regime, you should get martensite. This is an important point to remember because I'm going to show you something surprising in a minute. And the A1 and A3 temperatures are shown there off the phase diagram. We already talked about the two heat treatments. If you're lucky enough to find a continuous cooling transformation diagram for this, this shows what happens under non-equilibrium conditions, because the phase diagram, of course, is an equilibrium diagram. But pretty much the hardenability, the location of the diffusional transformation curves are way out here in time, like into tomorrow, so that at pretty much any cooling rate, you'll get a structure called martensite. We'll then go back and normally we'll temper that after heat treatment, and you can get it at cooling rates down to as slow as 0.05 degrees C per second to avoid forming the ferrite phase, which you normally wouldn't want. Remember this phase diagram, and remember this cooling, continuous cooling transformation diagram. We used an EOS M280, so it's referred to as a powder bed, as opposed to the company I work for is a directed energy. Directed energy is a lot like laser welding, and you shoot powder into the melt pool. This is actually, I'll show you in the next slide or the slide after what's going on. The beam moves very quickly. The beam is moved in this case over a thin layer of powder. It's difficult to see here, but you can see the beam moving here. It's directed by galvanometer mirror, so it moves very quickly. The laser power is not very high. The layer of powder here is on the order of 40 to 50 microns in depth, so it's not that deep. The way this works is sort of shown here. There's a thin layer of powder taken from a supply and squeegeed, not really squeegeed is not the right word, it's spread a very thin layer across the build plate by a wiper, which is usually ceramic or metal, and the beam then rasters over the part in a pre-programmed way, and then the middle box is let down by 40 microns and another layer of powder spread over it. And this continues until you then build the whole part up, and then it's buried now in all this powder, and you take the powder away and you have this, in this case, this chest piece here. And you do this over and over and over again by a layered process. And this is trying to show that there are the sort of three boxes. The box with the powder in it lifts up and spreads over. The box with the part in it moves down, and then there's a third box here where the overflow goes in. And the powders can be recycled if you want, and you're clever about it. So the procedures we used here, so there were no published procedures on this steel, and in fact, when you buy an EOS, you can make anything you want as long as it's stainless steel. Having the stainless steel dongle, to buy other dongle, to do the universal dongle costs you lots of money. So you can go in and do parameter editing. So we had that, but we had no idea where to start. So we did a range of parameters, and I'm having a hard time reading this. Is a bit of an eye chart. Different travel speeds, hatch overlapping. Whoops. Hatch overlapping like the welding passes. and power, travel speed, and hatch overlap, basically. And in a matrix of 25 welds, there is actually not a number 13 because there was a bolt hole right there. So the middle of the design of energy, the design of experiments, excuse me, the middle of the design of experiments data point was supposed to be right there until we realized that there was a bolt there and couldn't make that one. So we had this 5x5 sort of matrix and then began to look at the effect of the parameters on what we're looking for is full density, first of all, and then our properties later. So we looked at the phase diagram a minute ago, and I made a point to remember the continuous cooling transformation diagram because that was important, because this material we would expect after processing it and coming back to room temperature, we'd have all this martensite, which we would then go back and temper. Well, big surprise, we have none of that pretty much. So I'll show you the as deposited material. You can see that there is this pattern of contrast, layered contrast here, some interesting things going on. I have the next slide is actually probably the most interesting one. But we can see a number of different, so we can see the different layers, and at the bottom of each layer there's this dark contrast. We can see here a solidification boundary of a single AM pass. So we do, in any given layer, we'll do bunches of passes. They're parallel to each other. The next layer will be put down at an angle of, I think, is at 67 degrees. So it never repeats, it just continues to cycle. And so it's difficult to interpret some of the microstructures here. You see some columnar grains with cellular microstructure in here. And then you see these little regions here, these fine grains. The guys ended up calling that the speckled region. And there's some interesting reasons why that looks speckled that can be seen better here. So this is a higher magnification of pretty much one of these right here, this region in here. And we can see several different regions here, as I said a moment ago. So here's the boundary, for example, a boundary between the given additive passes. We can see there's some grain boundaries here they're decorated, or they were decorated with carbides until we etched them. We etched them with, we were not allowed to use a picric acid at the lab because they felt it was not safe. And of course, the Department of Energy wants everything to be safe. So we ended up using an etchant that's normally used for stainless steel. And it ended up removing the carbides from the grain boundaries, but they, I'll show you those at higher mag in a minute. There's also this blocky phase. So here, featureless kind of blocky phase. That ends up being in the near heat affected zone. I'll tell you how I got to that conclusion in a minute. And then there were these little fine grain regions here. Is that a number 4? I think I can barely see that here, but all this purplish looking stuff, these little fine speckled regions, that ended up being in the far heat affected zone. How did I come to that conclusion? I'll show you that in a minute. If we look at in SEM, so when we first saw these opticals and we're looking for martensite, which has a completely different microstructure, this was all a big surprise. And so did we buy the wrong powder, or are we just like the first people in history that can't make martensite properly, or what's going on? So at this point we were like very confused. Look in the SEM and we see stuff at higher mag that looks a lot the same, except we can see some of these other things here. So looking at this little region here at higher mag, you can see, ladies and gentlemen, you can see the solidification structure in the background there, right? You can still see it here as well, the cellular structure we spoke about. Irrefutable evidence of solidification. Now, why is this weird in steel? Can anyone tell me? In pretty much every steel, there's a solid state transformation that'll erase this solidification microstructure, and you never see that at room temperature. Yet we still see that right now. That's an important clue later. But we can see that here as well, around that little region, solidification structure. And then within these regions here, you see this lath-like stuff, right? And it's reminiscent of martensite or bainite. But it's only within that little circle, or this little region here and here, right? Otherwise, it looks like solidification everywhere else. Okay, still lots of confusion, what's going on. Next, we can do backscatter electrons. So this shows more Z contrast, but you can still identify, I hope you guys can see some of the things again that look like lathy regions in there as well. Electron backscatter diffraction, this is an SEM-based diffraction technique, and we've done a number of things in image quality and then this kernel area mapping. I won't go into a lot of detail on this, but the green color in the kernel area mapping indicates that there's a lot of sigma 3 boundaries. This is a low angle boundary using the coincident site lattice or CSL nomenclature. It's likely martensite. The image quality is also lower in those regions because the martensite is strained. That's another kind of clue for us. So how did I reckon that what was going on, the two funny regions we saw, the featureless region and the speckled region? I was able to conclude how those developed by taking one of the deposits, and I put, you can see here, overlapping laser spot welds. And then looking in the overlap region at these things here, you can see now the problem with looking at that one microstructure when it was all those were together were those featureless region and the speckled region, were those formed as I was making that little weld pass, or were they formed later when that weld pass became the heat affected zone of all the ones around it? Couldn't tell. So this was meant to spatially isolate what was going on. So if you look at the back end of one of the pulse boundaries here, you see that what begins to happen here is this featureless, you can see things that are reminiscent of this featureless region, and then also things that are reminiscent of the speckled region that we saw before. It then sort of suggests that there is a low temperature and a high temperature heat affected zone. This, in steel terminology, the low temperature one would probably be referred to as an intercritical. The featureless region is a higher temperature heat affected zone. Not exactly sure what's coming out right there yet, but it allowed us to sort of spatially separate and know the geometry was going on, and to realize that the speckled region, the featureless region, in that big, when I showed you the big yellow micrograph, those are formed in the heat affected zone of a given pass when a subsequent pass is made. So in the TEM analysis we looked at, Lejeune, here's those 952. So we saw these funny platelets that are shown here, right? And you can see them, these platelets here are at 90 degrees to each other. And the young man who did this was a postdoc at the time, and I asked him to tell me what zone axis we were on, and he never did. He found that the plates were oriented relative to the matrix with an orientation with a habit plane of 952. And he said, oh, this is one of the orientation relationships you find in high carbon steels, the habit plane. And I had to break his heart by telling him that habit plane of 952 is between the martensite and the austenite, and this is ferrite. So that's not quite right, but there's a very high distribution or very high density of dislocations all over the place. From a radiation tolerance point of view, if this microstructure is stable, and that's kind of a big if, there's many sink sites here for point defects. So when you irradiate something, you will often in a reactor, when the neutrons hit it, you will form point defects, Frenkel defects. You'll knock an atom from the lattice into an interstitial site and leave a vacancy. That's called a Frenkel defect. And these defects cause hardening and radiation damage, which then change the properties of the material. So if you can find regions where you can remove those from the matrix, and if that interface between the matrix and those little needles is incoherent, it can actually suck up those defects and you will have less damage. But this microstructure here is still not as good as you would find if you had a martensitic structure. This same young man also did this TEM bright field, telling me that, and I don't really see much except dark and sort of mottled, but he believes that there are dislocations and subgrains of what he thinks are martensite platelets that I've yet to see, and I still want him to go back and redo this sort of thing. But similar features are seen in the wrought microstructure, the martensitic microstructure. But and this microstructure, again, if stable, would be useful for radiation tolerance. I won't show you, oh yeah, so I won't show you the direct tempered. So as deposited, you went back and direct tempered it. Well, you temper martensite. If you don't have martensite, you're not tempering the martensite, and all you do is forming bunches of carbides, which is not really exciting. So I'm going to skip that altogether. The as deposited, very confusing. If you then take the material and go through the normal heat treatment you would go through for a raw material, including this normalizing, which again is reaustenitizing, dissolving the carbide, and then rapidly cooling, and then tempering, you get exactly what you're supposed to get, and this is characteristic of the microstructure you see. This is not high enough mag, but the microstructure you see here is characteristic of martensite, which is what we expected in the as deposited microstructure. It's fine grained. It's actually better, smaller grained than the wrought material. And in fact, I think I have some TEM here, but this is actually probably better than the wrought material from an irradiation tolerance point of view. Before I mention to you what happens when you etch with the etchant we used, so you see the grain boundaries here. There's little holes there. Those were where carbides used to be. They were chromium carbides. The etchant we used removed the chromium depleted region and caused the carbides to fall out. This is called ditching, basically, in corrosion terminology. So you see that there was lines of carbides along the boundaries, and then on the grain interiors, those are all gone. But believe me, they were there at one time. The electron backscatter diffraction results are exactly what you think it should be. You have all green in the kernel area mapping, indicating that it's likely martensite. So everything here is pretty much as we would expected, and completely different than what we saw in the as deposited microstructure. So, and then also here is some more EBSD data. Basically, it looks just like the wrought material. Okay, yeah, so here's some of the TEM stuff again. High dislocation density, fine grains, carbides on the grain boundaries. And this looks much like the wrought material, which I won't show you. CSL boundaries, again, is a coincident site lattice boundaries. And the point to notice here is that the quenched and tempered, which will be in the green over here, there are boundaries, sigma 3, and I think it's a 9 or a 10. Those are all characteristic of martensite. So there's tons of martensite in the quenched and tempered, as there should be, and not in the as deposited. If this figure were here, and I can't find this figure anymore, but if this figure were here, this is high energy density, high energy XRD, X-ray diffraction that was done by our colleague at Brookhaven. It allows you to separate in martensite, which has a body center tetragonal structure, the X-ray peaks would overlap for the two regions because of the slight tetragonality. This high energy XRD allows separation. The point to make here is that this process believes there's something on the order of 15 to 19% volume fraction of martensite, which we actually believe to be true, and most of that is in that speckled region we looked at earlier. So to summarize our microstructural features here of the three different sort of conditions, the as deposited condition, this is the big puzzler here. The solidification microstructure largely persists. There is a low volume fraction of martensite in those speckled regions where we saw the lathy structure in the SEM micrograph. There's few or no precipitates. There are regions in those speckled regions of martensite, little pockets, and the microstructure is very homogeneous. I said the tempered looks just like the as deposited, except a lot of more carbides. And then the normalized and tempered looks exactly as you would expect a wrought material to look, and as we expected the as deposited. High volume fraction of martensite. There's carbides on the grain boundaries and the lath boundaries. There's a high dislocation density and small grain size. The microstructure is very uniform. There is tiny, like 5 nanometer size pores. I won't show you that, I don't think, but it's not too exciting to see those. So here we see a whole bunch of interesting stuff going on. Still haven't told you yet why the as deposited evolved, the microstructure evolved that way. So let's talk about that right now. Who wants to help me guess why the microstructure turned out the way it did in this process? Gentry's making a funny face, like he's confused.
Was it for all the samples that you tested? It was consistent that
All,
there a trend associated with the parameters you used?
All 25 minus number 13 showed very similar. The volume fraction of the different regions differed a little bit, but no, mostly over the entire region we did this. And they were mostly all fully dense. Not all of them were fully dense. In fact, sort of that square, the lower left corner was less dense, and then the high upper right corner was fully dense. So those are the ones we concentrated on. But the same microstructures were present across the whole range, whether they were fully dense or not. And even outside that range, because I went back later and did some other stuff outside that range. We checked the powder composition, we checked everything we could think of. We stood on 1 foot. It still came back the same way. Okay, so that's fine, because I'm still confused. I was confused for months. So we see, okay, microstructures of the as-deposited sample, I think you'll agree, were varied and confusing. We see the evidence for solidification can be seen, and there's at least one type of carbide present in the microstructure. If you go to literature and look for dendrite arm spacing versus cooling rate relationships, you won't find one for this material. You can find them for stainless steel, which this is not. Okay, this is a 9 chrome. Stainless steel has a minimum of 12% chrome. But if you go use some of those numbers, you can estimate maybe solidification cooling rate. You can also use the numbers for steel, which have a cooling rate as a function for dendrite arm spacing, primary dendrite arm spacing, as a function of carbon content. If you use those two, which neither of which this is, but if you use those two, you get a number on the order of 10 to the 5th K per second using published results for primary dendrite arm spacing, right? So it appears something going on here leads to development of unusual microstructures. Hold on. I probably should have put that slide before you. So let me go here and I'll go back to that slide. This is these are optical micrographs of a similar grade 91 steel powder made on the lens. This is the Sandia designation, laser enhanced net shaping. This is the company I work for now, without heat treatment. So this is a different type of additive. Did not have anywhere near the cooling rate that the powder bed had. And what do you see there? This needly-like microstructure is characteristic of martensite. So it is possible with other processes involving additive to get the microstructure you think you should have. I probably should have put that first before this. But it appears that this really rapid cooling, and I think the cooling rate in the micrographs I just showed you a moment ago, probably on the order of 10 to the 3, maybe up to 10 to the 4. But it's hard to tell because I don't have dendrite arm spacing to measure and estimate from. But it's much slower cooling rate. So something about this rapid cooling rate seems to produce these interesting microstructures. There's also the notion, as I said before, about when I saw those interesting regions, did they occur during the production of that layer, or do they occur as the subsequent layers were put down? So that it should be borne in mind that the microstructural evolution that occurs during this should be interpreted with a view towards multiple thermocycle effects that they can also impact. And I'll show you on the next slide a graph of that. So as I mentioned, the microstructures of tempered samples are consistent with, they look just like the as deposit except a lot more carbides. And the normalized and tempered looks exactly as it should. And that would be an interesting microstructure to get. The local thermal cycling that you'll see, this is like a multi-pass weld, right? So here is my location that I'm going to reference to. And if I think about time versus temperature, and this is the sort of T of the preheat, this is the solidus, this is the liquidus. Obviously, to melt, I need to go above that. But as the beam approaches during the rastering process, the powder, which is just sitting there loose initially, we'll see several thermal cycles, and then the melt and resolidification cycle, and then several other cycles afterwards where it's solid, and this is where the heat affected zone will form in the prior layers. So we need to kind of bear this in mind also, and that was an important thing we talked about a little while ago with the other 2 heat affected zones. So back to the phase diagram, and here's the whole punchline of the whole presentation. So Cooling rates, as I said, we think are in the order of about 10 to the 5th K per second if you believe all this. Under equilibrium conditions, the phase diagram tells us we should undergo this sequence of phase transformations, which we don't see microstructures consistent with that. We see something different. So if we go back and look at the microstructures and bear in mind the little spot weld experiments we talked about, plus the thermal cycling, what it looks like is the structures that are formed, I can't tell you why, but are consistent. The interpretation is consistent with rapid cooling through forming liquid plus ferrite and then ferrite, but rapidly cooling through this region here, the two-phase ferrite plus austenite, austenite two-phase austenite plus carbide, down here into the alpha. Now, delta and alpha are just designations for the high temperature ferrite phase, BCC phase, and the low temperature BCC phase. So apparently what happens, or one impossible interpretation, is we solidify, we actually will undercool as occurs in rapid solidification. It seems that we fly through the region where the austenite is the matrix, is the stable matrix, and form very little austenite, and that's why there's no martensite, because to get martensite you have to start with austenite. It cools apparently very quickly through this region. Now the 10 to the 5th is the solidification rate. The cooling rates through this region are probably fast-ish, probably not as fast as 10 to the 5th, but fast enough, so that it seems to bypass forming any austenite, which is why we don't see the martensite. And then once the structure reaches this lower temperature BCC phase, there's no more driving force thermodynamically to continue to transform to austenite, because it's now back into a region where it wants to be BCC. So this causes the solidification structure to remain with a very few carbides. And then as we do these multiple thermal cycles, the featureless heat-affected zone will occur, and then the other heat-affected zone, the speckled region heat-affected zone where there's little martensite grains, also occur. And that's kind of what seems to happen. Thermodynamically, does that make any sense? Can I prove all this by any calculation? Lejeune thinks we can, and I'll await that to see. But at least the structures are consistent with this story, if we don't know why. How are we doing on time?
30 minutes.
A long time? Okay. Oh, okay. So we'll talk a little bit about the nano indentation. So it allows us to do, and I'm not a nano indentation person, so this was a learning experience for me, but you can get a modulus and hardness measurements of small volumes. You can also do hardness microstructure characterizations. We'll talk about that a little bit. And then when you're doing ion irradiation samples, you will get, so we will often do ion irradiation to mimic the neutron irradiation that's experienced in the reactor, to do it quickly and less expensively. And then the third and most important region is if you stick it into the reactor and it gets activated by neutron irradiation, you can't probably touch it for the next 7 years. So it's probably not a good idea to do a PhD on this unless you want to stay around for a long, long time. So you can't get to the parts or to the components then. So the ion irradiation, the downside is that it's a very, not a very deep layer of irradiation damage. So you can actually do ion irradiation surfaces and then look at other regions and compare the hardness and look at ion irradiation induced damage like we spoke about earlier, and see changes in hardness which will manifest themselves in properties in service. I guess the thing I really want to show you is this here. So we looked at the sample where we, as the positive or the tempered, you would see when we took the data, you would see, because this is basically the microstructure hardness correlation. So the little speckled region, if you put the nanoindenter into the speckled region, which has a lot of carbides and martensite, it would show higher hardness, and that is the red arrows there. So whenever they impacted or pushed down into the martensite regions, they had higher hardness, whereas The regions that were not the speckled regions had the blue, lower hardness typically. Again, that was a clue to us that that was martensitic. But the normalized and temper had a much more uniform response here, basically. Also, this is the only time we're going to talk about some of the radiation hardening effects. So I'm having a hard time reading this because this thing is in the way and I can't read it real well there. So the tempered and the normalized and tempered AM samples showed reduced radiation hardening as compared to the as deposited one. So the as deposited one, you're looking at, I got to go back and look at this again. There's a difference in hardness, and I think he's trying to show here that, well, that's not difference, it's just absolute. Okay. So the as deposited at 30 dPa. dPa is abbreviation for displacements per atom. So atoms that are ion irradiated, the atoms were displaced and moved by radiation damage cascades 30 times and experienced much higher hardening. So they will be much harder, they'll be less ductile, and so their service life will be compromised in this condition. That was for the as deposited. The one that was normalized and tempered, which I can't see, normalized and tempered here, and then the wrought, so a piece of wrought that we just heat treated, wrought meaning it was cast and then rolled. You see that the normalized and tempered and the wrought have very similar properties, and in fact, if there's anything, the AM normalized and tempered had did not see induced irradiation damage hardening as much as the wrought sample. So it actually ended up, if anything, being better than the wrought material. So there's actually great promise for this. If we this method, if we want to, if we can find a way to commercialize this. I showed you this before, and I guess I should put that in different order. This is what I talked about at the very beginning. This is not cut off the surface. You can see the build plate here still underneath. This is a, you can see the tensile samples in between in the little middle here. This is only about 3 inches tall. It was supposed to be about 5 inches tall. The wiper blade broke on one of these tensile samples like 90 hours into this build. So that was like 90 hours of build time. And then there's other samples around the outside. And this was, we didn't have the CAD drawing for this. So this, the set of holes is supposed to match up seamlessly, not have this continuity here. But this was built on the powder bed machine in about 90 hours. And this is a simulated heat exchanger. The holes are all the same size, but of that same grade 91, this now sits on the funding agent's desk in DOE headquarters, and he won't give it back to me because he gave me all the money, and I figured it was worth the money to give me, but I wish I still had this. So these are the sort of things that we can try to build. This is kind of a simple geometry, and it's nice because it's axial symmetric, and the movement in the z-axis is not really complicated. You can do it with a 3-axis machine. The manufacturer I work for now has 5-axis machines, so we can do much more complicated things. So I think with that, I'm going to stop and slow down here. Conclusions. We've gone through this before. Surprisingly, we found little martensite in the as deposited samples, with those exceptions of the speckled region. This was indeed unusual with what we expected according to the continuous cooling transformation diagram. Something about the rapid cooling rate leads to yet to be determined non-equilibrium conditions, which give us this interesting microstructure. There's an epilogue to this too, I'll come back to in a moment. The existence of this solidification structure, which is clear and unambiguous, and the lack of carbides, lack of oodles of carbides in the room temperature microstructure is further evidence for what happened there. We must somehow skip that austenite phase field. But we can achieve martensite if we go do the normalizing and tempering, and that in and of itself was very useful to do, even if you just take advantage of the advantages of additive by itself. I think there's another group here. Okay. The normalized and tempered was consistent with anything you would expect it to happen. And as I mentioned, Typical of steels, when you do the normalizing in temper and you do it in a slow way during heat treatment, all evidence for the microstructure, the solidification microstructure that remained in the as deposited were erased. Characterization of the normalized and tempered samples shows that it has the microstructure has very good radiation tolerance properties, and similar microstructures, I guess. I think with that, I'm going to stop. I can answer questions, but I would also point out, I can now tell you, because our provisional patent is being filed tomorrow, and I'm pretty sure none of you can repeat this before tomorrow, that the interesting microstructure we saw in the as deposited samples, we thought at first, like, man, this was like something we screwed up. I did not get follow-on funding for this work, which was really a bummer. But the cool thing is, the following year, when we started to do some things with this, we started to look at high temperature properties. There was a young man from DOE headquarters who came to do his PhD at LANL and came to LANL for on sabbatical. And he was putting diamond into copper to increase the thermal, or carbon nanotubes into copper to increase the thermal thermal conductivity. He saw this stuff and says, oh, hey, Dr. Lienert, can I work with you for free? I'm already paid for. I said, great, what do you want to do? I'm an ME, I don't know anything about materials. I'm like, great, can you do the tensile testing? Sure. So he spent the summer and the fall, and he ended up not just doing the room temperature stuff. He said, well, I'm going to take it to 600 degrees C. I'm like, you're not going to find anything interesting. I was wrong. He found something very interesting. At 600 degrees C, this microstructure of the as deposited sample had much higher yield and tensile stress than nickel-based superalloys, which are much more expensive and are used at that temperature. That was not impressive initially until we started aging them. We are now up to 1,000 hours of aging, and then we go back and test these at 600 degrees C. And they still have way better properties than the nickel-based superalloys that are used in many applications at this temperature. Now, 1,000 hours is promising, I'll point out, but when you realize that the reactor lifetime is 50,000 hours or more, 1,000 hours is not a lot. I keep expecting the properties to fall off, and in fact, I had a bet that after 100 hours they would be like butter, and I was wrong. So I had to buy that guy an orange juice. But it was worth the orange juice. So the patent's going in finally tomorrow, about these really interesting properties. We still have no reason, we have no understanding of what's going on, but they have really cool properties. And I'm not even sure why that's happening either. We haven't done the characterization yet. So there's maybe a happy ending there. We'll file a patent, and then we'll go back and try to figure out what's going on. So that's actually kind of cool. The other thing is, yeah, this additive stuff can really be useful in nuclear energy applications. There's a much more recent development. There are several nuclear reactors, like big-sized, huge-sized nuclear reactors being built in the States. And they've been on hold, but there's some of them that have been recently given permission or permits to continue. The problem with additive is I don't have like a 10 meter by 10 meter by 10 meter build volume. So there's now these smaller modular reactors, which are cool, and then these little microreactors. Microreactors are not meant to be commercially viable. They're sort of in case of emergency. Instead of having your little Honda generator, like when your hurricane comes and and that's how you run your lights. The microreactor is sort of meant to do that. The small modular reactors can run little cities, but now the cool thing in the States is, in case of a nuclear attack or someone attacks the power grid and the power goes down, the people at NORAD can say, the NORAD missile controls and all the other defense agencies can claim, well, we need a small modular reactor that we can park in a bunker nearby so that we can respond and blow up the rest of the world, or send our bombers to blow up Russia, so we have the power to do that. So it's no longer, as Patricia and I talked about yesterday, it's no longer a concern of a lower carbon footprint. It's we are now, the Department of Energy is using human nature against the Department of Defense and saying, well, if NORAD gets one of these, then we'll make another one for the Strategic Air Command and for the Pentagon. And so once you start finding out that your neighboring military installation has one, you're going to want one too. So economically, there could be a big boom in these. The other cool thing is their volume, this hexagon I showed you, that hexagon can be put into a small modular. It's a little bit smaller than it should be. It should probably be about twice that size, but it can be used in a small modular reactor. I have build volumes that are reasonable enough to make these things. I can't make the 10-meter size stuff, but I can make these sort of things. So that's also exciting now that, so the reactor sizes that are probably you're gonna see in the future are gonna be much smaller and opens up a lot more latitude for this technology to be used. So I said I was gonna shut up. You can ask technical questions if you want to ask me about AWS, or you want to ask me about being president of AWS, or even working at LANL. All those questions are fair if you wish to ask as well. So thank you for your time.
Dr. Tom, I'm sure we'll have some questions.
I have seen some retention of data ferrite with an architecture. Some retention of data ferrite. I have seen some in the micrographs.
Retained?
Retention of data ferrite.
It's difficult. Usually you work for Lejeune, no?
Yes.
Okay, so.
You mentioned that one of your micrographs earlier, your slides, part of it to us is retained delta ferrite.
Yeah, here.
Yeah,
The
these are
boundary
those
of
smooth
the
ones.
first one.
Yeah, very smooth ones.
Yeah. That's data ferrite.
How do you tell it's retained as opposed to it's now in the alpha phase field?
Because the cooling rate is like too fast. So like at the time of like transformation from data plus austenite, so there is no transformation fully from delta ferrite to austenite there.
So I'm sorry, so tell me where you think is delta ferrite?
At 1.1, there is a boundary of delta ferrite in martensite.
Which number one? Here.
0.1, that part you are at the top, above that. The smooth phase, yeah, this one.
This here you think is retained?
Yeah, this is
I think that is the high temperature heat affected zone. So whether it's the ferrite, high temperature, or austenite, it is now ferritic now. So when you say it's retained, it occurred during reheating and cooling, and that's why it's retained? Okay.
like delta ferrite like at high temperature, but that's not going to transform in the austenite.
I think it's all delta ferrite at one time that is now retained. Even the solidification microstructure was delta ferrite, is now alpha ferrite, and then it becomes sort of a semantic argument over whether it's delta or it remained from high temperature, yes. Usually when you see retained austenite, you see little islands or slivers.
Composition at the boundary, like the smooth phase and the other phase.
At the face right here?
Yeah, there's some composition variation, like there's delta ferrite is there, so chromium and the manganese is also going to like increase at composition and at that phase.
At this interface.
Yeah. And hardness is almost about like very much difference in the
So
hardness also.
what I didn't show you is that at those interfaces, there is a precipitate free zone. So if you look in here, you can actually see some carbides in this featureless region. Do you know what a precipitate free zone is? PFZ? Yeah. Along that boundary is a PFZ. I didn't show that. There's a whole bunch of stuff we couldn't talk about today. I didn't have time to talk about. So, but you believe the whole thing to be retained?
Yeah.
You say it's primary ferrite, right? Came from solidification.
I don't think this, so this solidification zone, this region is the heat affected zone of this other pass right here. I believe this and this and this are heat affected zones of the next passes, right? Where you still see the solidification. Do you see the cellular microstructure? That's the solidification region. This results from, and the same thing down here. There's along that grain boundary? that it's not as big as this blocky region, but you see this blocky region along the grain boundaries here and here. That's when that pass becomes the heat-affected zone of the next passes. So
You have the S deposit and the ESD. At the higher mag, we'll probably be able to find where the delta ferrite is.
I'm not disagreeing. I think we get into a semantic argument. I agree it's delta ferrite. I don't think that the blocky region melted and re-solidified again, because it would still have a solidified microstructure like the original did. But in here, yeah, this is meant, Lejeune, to show basically the very small speckled tiny grains. Those are not individual carbides, those are individual tiny grains of martensite. And that's why they have the image quality, contrast, and the cam map color that they do. I mean, I understand it's ferrite. It's probably delta ferrite, but it's not retained ferrite like you think of when you think of grade 91 normally in little islands because of regions of segregation or whatever. It's a little island. These are much bigger and more continuous. So we may be having a semantic argument right now. So I don't know. Are you saying anything different than I am, I guess, is what I'm trying to understand. Okay. I'd be happy to talk about it some more if that would help. In fact, because you apparently know more than I do on this, so that'd be helpful.
This is wonderful. Have you checked the crack tendency during the deposition, where you avoided the martensite that you don't run into cracking at all?
Whether it's lens, DED, or powder bed, there was no cracking at all. No.
That's one of the, I think it's most significant outcome.
You mean, wait, so solidification cracking or type 4?
It's just as deposit for P91, if you don't do it at the top, it's a full crack.
Right. The type 4 cracking, right. So none of, as we spoke in the office, I was concerned about that potential, and in fact, that was in the proposal, where they ask you to, like, what is your risk mitigation, right? I'm like, well, nothing can go wrong because it's going to be martensite, right? Well, it could be type 4 cracking. So I actually put that in there, but then I said, oh, additive, it won't happen in additive because additive is magic and super or whatever. But I put that in because if you sound too cocky, like, well, there's no risk in this at all, well, it didn't crack. But all the other expectations of how hard can this be? It's going to be martensite. This should be trivial, right? Well, all those were smashed. So this was actually a very interesting learning experience. I was really pissed when I didn't get the follow-on funding because I couldn't explain the microstructures, but then when we got the extra funding the year after because of the cool properties, that sort of made up for it. Yes?
What was the build delay temperature during deposition process?
I'm sorry, the build
delay temperature, did you?
Preheat? Yeah, I'm sorry, it was 200 degrees C. The build plate was set to 200 degrees C, which would normally slow the cooling rate down some, yes, but no, did not. I mean, it was still fast enough.
So you didn't compare that with other build delay temperature? For example, if your build delay temperature is lower or higher,
so it's a good question. I did not. On the EOS, you can do no preheat, 100 and 200. You have your choice of any three you want, as long as it's those three. And the dongle will not allow you to do. Now, we could have done other things because we had the magic dongle that would allow us to go in and do all the parameter editing. We did not do that. During the initial 6-month period, I was just more concerned with understanding what the heck was going on. And in fact, up until 2 weeks before the defense and please give me money for phase 2, I was completely confused. I thought, like, we mixed up the powder. It was, you know, anything I could think of to figure out, and I still couldn't figure it out. So finally I just said, this is really cool, this has never been observed before. And they're like, yeah, but it wasn't what you wanted, so no more money. So I would like to go back and try that. The lens system has a much different cooling rate though, so it is possible. And the fact that it's possible with the lens DED at much lower cooling rates, that we don't suppress that austenite transformation, that's another hint as to what's going on. Yes?
Dr. Thomas, do you think that the presence of the dendritic microstructure made your sample more resistant to the radiation, or would it have been better if there had not been the dendrites?
So the irradiation tolerance, I should explain. Actually, let me go stand at the microphone. The improved radiation tolerance occurs because the lath sites in the Martin site act as sink sites for the damage, the vacancy and the interstitial C substitutional. There's also not hydrogen, helium, a daughter product form. So the Martin site lath boundaries are what really help you with that, because they're low angle sigma 3 boundaries. They will act as sinking and trapping sites and recombination sites. So you saw from the nano indentation results that sample did not have, it had much greater radiation hardening than the normalized and tempered, and then also the normalized and tempered rot. So I don't believe that the dendritic or the cellular microstructure helped in any way, no. Yes, sir. Dr. Wood.
So I don't know much. I know a little bit about these materials. I've seen presentations over the years about creep failures associated with P91. So the strategy of doing it with additive manufacturing essentially means that like the whole structure becomes a heat effector, which could be susceptible to some of these type of creep failures. Have you looked into that, and what have you found?
No, we haven't done the creep yet. This is a creep-resistant ferritic martensitic steel. And we haven't done that. That was where the follow-up money was supposed to go. But we haven't done that yet, no. So I think, in fact, what we're doing now, we have money from the same office of DOE to do DED additive. I can tell you now because we have the money and we have the equipment to do it, and I don't think you can do it by a couple months from now. So preheating with high heat and then using real high heat input to do, if you're familiar with temper bead welding, when you're arc welding, to essentially if you can do the same thing and you can end up with the tempered hardness and microstructure that you would do if you, the problem with trying to temper this now is that you can't take that whole reactor and stick it in an oven. So you've got to use the big heating blanket, and it's a big pain to do all that. If you can have it end up at the end of additive that you have fully dense, your thermal cycles are such and your spacing are fully, you get a fully dense deposit, and your heat input and perhaps preheating is sufficient to cause tempering of the prior beads exactly as you want it, then there can be advantage in doing that, because you would normally go through this direct temper as we spoke about earlier. But Lejeune is talking about the type 4 cracking that occurs in the, what is it again? ICHAZ, intercritical HAZ, which I think is where the Martin site pockets come from in there. So I don't know the full answer to that.
I'll stay.
I have a brief question. So
Sure.
You showed us a CCT, right? Like real underspiralities. Now, that CCT is kind of misleading because it makes you think if you move all the way to the left, you're always going to have Martin sites, right? So there should be some correction. I don't know how to measure that, right? That says that at some point, no, you don't have the Martin site finishings, right? And you go from liquid to delta straight.
Well, so yeah, what I'm trying to do, this is what Lejeune and I spoke about in his office too, is I asked to borrow his Porter and Easterling because there's an interesting series of continuous cooling for the aluminum precipitation hardening and aluminum copper. And I was thinking about this on the plane, and I'm like, I wish I had my copy of Porter and Easterling, and I said, oh, I know who will have one. Lejeune will have one on his shelf. And he did. He had the green one. I have the blue one. He has the green one. But it's a bit misleading, yes, but it's not also because it assumes what does this diagram assume? That up here I already have austenite, right? So if I don't have it, it's not there. Now, what I really want to see is a stack up of C-curves like this. It would be awkward to try to use the solidification transformation in a C-curve because I don't think it follows that. But of these other transformations that occur all the way through here, each of them will have a C-curve. And I'm trying to figure out how to displace them in time it's not a proof, it's a visual aid to understand what I'm trying to say about the sequencing of missing the nose of the austenite curve or just touching the nose of the austenite curve. It's actually a visual aid, but I kind of wanted to find a series of these sort of things where this C curve would be here, the other one above it and other ones below that, to try to illustrate that, yeah, if you don't have austenite, you can't have martensite. And so if you've actually blown through the austenite one, which is above here, 6 feet above the ceiling, if you blow through that one, you have no, then this has no meaning whatsoever, basically. Am I answering your question, or am I just confusing things?
Well, what you're saying is this sucks for us. We should start at coloritic temperature or liquid temperature for what we care.
Right, and so this is what Alex is doing with his stuff, right? Is on heating, and if you don't have, this also is homogenized up here as well, right? Not only is it austenite, but it's supposed to be homogeneous austenite, and if they're correct, they will actually tell you, as they do, right? They tell you what the ASTM grain size is and the austenitizing temperature and time, because that really matters to the position of these curves here as well. So I won't say it sucks. It's awkward. It's clumsy. I'm having a hard time trying to find the best way to illustrate using such a diagram or a series of diagrams like this what I'm postulating the sequence to be. Again, that's not a proof in any way, but that sort of just helps people understand.
In comments, your thermal cycle actually measured?
No, the bad thing about powder bed is it's really hard to get to measure that, right? You can do that more easily. In directed energy, you can have the infrared thing above, you can have an infrared from the side. In powder bed, it's surrounded by powder, and you can't really get in there and do that very easily. I would not have a problem, as we talked, I would like to have someone like Debroy just run a model on this and give me an approximate order of magnitude of cooling rate. I'd be happy with that, because that's better than that dendroid arm spacing guessing thing. And dendroid arm spacing, you know this, but you got to take a lot of measurements, and unless you section, if you have a cylinder and if you don't section it along the prime meridian, you get a different number, and you assume that's the dendroid arm spacing. So for every one that's correct at the prime meridian here, there's one above and one below at equal distance that are wrong. So there's twice as many wrong at every, or more than twice as many. So you have to take a bunch of those measurements, hope that they're laying either straight on or that you're looking at them straight down, and make the measurements. If they taper because they're angled, so it's dodgy. You take a lot of data, and then you have to apply, I did not apply, then you have to apply a stereological correction to that for how many ones above and below are wrong. And it becomes super dodgy. It would be nice if we just had another actual calculated or measured number. Go ahead.
I wanted to know, AWS president, well, my understanding is most of them have like a signature issue that they tackle during that term as president. What's been your issue that you wanted to tackle?
You're right, and that most presidents have a single signature thing. And if you ask Patricio, I think he will tell you that I have a dozen. Future leaders is one, and Mitchell is one of those. That was one of my things. Diversity and Inclusion Committee is one of my things. We talked yesterday, Patricia and I, at lunch about our need for a real strategic plan as opposed to a pretend one. If my colleagues were here, they would get mad at me. That's also an issue. So I have too many. I don't have one. I have literally, and by the time you become president, you're told you better have everything done because you won't have time. And that's correct. I don't have a lot of time, but that's not stopping me from coming up with new signature issues.
All right. Any more questions for Tom?